Hello dear viewers. Now I would like to present the part 6, which is a thrilling and enjoyable journey through the world of measures of dependence. Take your seats and take the notes. At the beginning, the main idea of the measures of dependence. The measures of dependence are a unique group of statistical measures that shows the degree to which the values of two statistical variables are related. In other words, we are trying to capture the interrelationship between the values of two variables. For example, the interrelationship between the values of variable x and the values of variable y. The interrelationship. So I must stress that we don't define the causation effect. Yeah? We don't define which variable is a cause, which variable is an effect, like here. We don't do that. We don't know if x is a factor of y or y is a factor of x. We don't do that. We are interested in a interrelationship between both variables. So we follow the main question. In general, do high values of variable x are accompanied by high values of variable y? High and high values. In other words, do we observe, in general, of course, because we are talking about an overall statistical tendency. Do we observe high values of variable x and simultaneously high values of variable y? Or, in other words, as you can see in the bracket, do we observe low values of variable x and simultaneously low values of variable y, of course in general? And we can also meet the following situation. Do high values of variable x are accompanied by low values of variable y? Or inversely, do low values of variable x are accompanied by high values of variable y? We can also ask, do we observe, in general, of course, do we observe high values of variable x and simultaneously low values of variable y? Or do we observe, in general, low values of variable x and simultaneously high values of variable y? This is the quintessence of measure of dependence. We are trying to determine the direction, which can be positive, high and high values, low and low values in general, or can be negative. In general, high values of one variable and simultaneously low values of the next variable, or low values of one variable and simultaneously we observe, in general, high values of the other variable. We are trying to determine the direction and the strength of this kind of interdependence between the values of variable x and the values of variable y. Here we have the example of possible interrelationships between the pairs of the variables in the statistical procedure. First of all, we want to answer the question, is there any interrelationship between the values of both variables? And if there exists a interrelationship, the next step is to determine the direction and the strength of this kind of interdependence. Alright, but at the beginning stage, I want to visualize you the problem using a simple graph and this kind of examples. Let's imagine that in my simple graph I denote the household's income using X letter and luxury goods consumption using Y letter. Yeah, and I build this kind of simple graph. Here on this axis I put the values of variable y, and on the horizontal axis I insert here the values of variable x. Here we have income, here we have luxury goods consumption. And the first question is, what do you expect? If we expect that if we have high income, we will have high luxury goods consumption. Yeah, because it's a regularity that rich households consume more and more luxury goods. Yeah. So we expect also that poor households consume a low volume of luxury goods. It's a kind of regularity, yeah, like here. We can perceive here a statistical tendency, yeah. Of course, we can meet the households that have high income and low luxury goods consumption, yeah, because they are mean, yeah, and don't like luxury goods. It's possible, of course. We can also meet the situation where we have poor household, yeah, but they consume a lot of luxury goods in this household, yeah, because they take they take credits and buy luxury goods, purchase luxury goods using credits. It is also possible, yeah, because it is why I emphasize in general phrase, because we are talking about a general tendency. It is not always true, yeah, but a certain phenomenon here can be perceived, a certain interrelationship between the values of both variables, yeah. So here in general, high values of attribute of variable x are accompanied by high values of variable y. Yeah, so this kind of interrelationship is positive. In other words, low values of income are accompanied by low values of luxury goods consumption. Of course, in general, because we observe also abnormal observations, yeah, in which we have high value of a variable x and low value of a variable y, or low value of income and high value of luxury goods consumption. Abnormal situation, but general trend, general phenomenon shows us a positive interrelationship between both variables. And the next example is households income and inferior goods consumption. We will also denote inferior goods consumption using Y letter. You know what it is. This is, for example, inferior goods, frozen dinners, junk food, yeah, intercity bus services, potatoes, and etc. Yeah, we can use an analogous graph. Y, X, here we have inferior goods consumption, here we have income. And what do you expect? Of course, we expect that if we have high income, we consume less volume of inferior goods consumption. Yeah, like here. And we also expect that if we have low incomes, poor households, we will simultaneously observe high volume of inferior goods consumption. Yeah, if the household is poor, they purchase more junk food, fast food, market beers, frozen dinners, yeah, interbus service, and etc. And as you can see, a certain phenomenon, a certain regularity can be perceived here. Yeah, this interrelationship has a negative character. Yeah, because high values of inferior goods consumption are accompanied by low values of income, and simultaneously high values of income means low values of inferior goods consumption. Of course, this is a general phenomenon, yeah? In general, I must emphasize this phrase, in general, because of course we can observe one or more times an untypical household in which we have high income and high inferior goods consumption. Yeah, for example, they are rich but they love frozen food. It's possible? Is it possible? Yes, of course. We can also find a untypical household in which we have low income and low inferior goods consumption. It is also possible, but the general phenomenon can be perceived here as a negative character. Alright, you can try to conduct this kind of analysis using the next pairs. Alright, but how to quantify that there is a negative or positive interrelationship between the values of two variables? We need an objective criterion, statistical mathematical measures that indicates the direction and strength of interrelationships. We can use a following set of measures called covariance, denoted by symbol cov, coefficient of correlation, denoted by capital R or cor, which means correlation, and coefficient of determination, also called R squared coefficient. Alright, let's start with the first measure, covariance. Covariance is a generalization of the variance. It shows us the average product, the average, because we divide the sum by the population size. Here we have the average product of the deviations of variable x and variable y values from their mean, x mean and y mean, the average product of the deviations. We can also use the alternative form of covariance formula. We can transform that fraction into that relation, in which we have the sum of the product between the values of variable x and variable y, so the average product of the values minus the product of mean x and mean y. Alright, and the interpretation is following. If covariance between the values of x and the values of y variable is positive, then generally, as I said before, generally high values of variable x are accompanied by high values of variable y. It also means that low values of variable x generally means low values of variable y. And we can inversely use here variable y, here variable x inversely. Okay, let's imagine following situation. Here we have an appropriate graph. Here we have x axis and y values axis. We have two observations. x1 and x2, and corresponding to them y1 and y2. Here we have two objects, and first object is characterized by x1 value and simultaneously by y1 value. The second object is characterized by x2 value and simultaneously by a y2 value. We have two values, so it's very easy to indicate the mean value. The mean value of y, yeah, is placed exactly in the middle between y1 and y2. Here we have mean y value, and analogous, here we have analogous measure x mean, which is placed exactly in the middle between x1 and x2. Here we have typical levels, mean levels of considered variance. Okay, and let's talk about the deviations and the signs of these deviations. First goes variable x. The sign of the first deviation, x1 minus x mean, is x1 is lower than x mean. Yeah, here we have lower value, so the sign of this deviation will be negative, right? Simultaneously, we can wonder the sign of the deviation between y1 and mean y value. Yeah, here we have x1 and y1, the deviation between x1 and mean x, and the deviation between y1 and mean y. Here, this sign will be also negative because y1 is lower than y mean. Yeah? And finally, the sign of the product of these deviations, x1 minus x mean multiplied by y1 minus y mean, the sign of the product between something which is negative and something which is negative gives us positive value. Yeah, negative deviation by times negative deviation gives us positive sign. Okay, and we have also the second object, which is characterized by the following deviations: x2 by x2 minus x mean, y2 minus y mean. Yeah, x2 is higher than x mean, so the second deviation will be positive. y2 is higher than y mean as well, so it has also the positive sign. How about the product of the following deviations? Something which is positive multiplied by something which is positive also gives us a positive value. Yeah? And I will try to summarize the problem. The first product of deviations, as you remember, was positive. The second product of the deviations the second product of the deviations is positive. Yes, so the sign of the sum, yeah, maybe this is a square, it's this amount is equal to square. Yes, the sign of the sum, if I sum both products which are positive, the sum will be, of course, also positive. So the covariance between x and y, it has positive sign. Yeah, both products of the deviations are positive. I sum these products, both products, which are positive, and I will receive, of course, a positive sign of the sum. So the covariance will be positive here. All right, and we can also consider another example in which we have the following situation. Here we have x1 and corresponding to this value, y1 value. Here we have x2. This object, the second object, is characterized by x2 value and y2 value. And now we expect a negative interrelationship between the values. Yeah? Oh, sorry. What we can say about the signs of the deviations? x1 minus x min is negative, yeah, but y1 minus y min, y1 is higher than y min, is positive, yeah, and then the product of these deviations, in which we have one negative and one positive value, will be negative. Yeah, will be negative. Let's wonder another. Let's consider another object. x2 minus x min. This number is higher than number. So here we have positive sign, but y2 minus y min will be negative. And the product of both values plus multiplied by minus gives us minus, of course. x2 minus x min multiplied by y2 minus y min is negative. Yeah, this number was also negative. We sum up something which is negative in both cases, so this sum will be negative and the whole covariance will be negative. Yeah, and this is how it works. Sometimes we can meet the situation where we don't see any regularity. Yeah, any regularity. We can encounter both high and high values, low and high, high and low, and high and high values. Yes, in that situation, covariance between the values is approaching, is close to 0. The next measure is one of the most important measure in statistics, it's coefficient of correlation. Coefficient of correlation, full name of this measure is Pearson product moment correlation coefficient. It is a standardized measure, and apart from the direction of the interdependence, gives us information about its strength. Yeah, remember that covariance indicates only the direction of the dependence, interdependence. Correlation coefficients gives us also information about its strength. R coefficient takes only the set of values from -1 up to 1, yeah, with -1 and 1 value. Covariance takes the real numbers, yeah. So this is a kind of standardized measure, yeah, because covariance can't be higher than the product of standard deviations, yeah, of variable x and variable y values. It takes only the values from -1 and 1 with -1 and with 1, and the features of this measure are following. The closer R coefficient is to endpoints, yeah. Here we have endpoints 1 and -1, here we have 0. The closer R coefficient is to endpoints, the stronger correlation we have, the stronger linear correlation we observe. Yeah? The stronger correlation. Values around 0, the closer the values is to 0, the weaker linear relationship, the weaker correlation between the values of the variables we observe. Yeah, higher end-to endpoints, weaker, close to 0. And if coefficient of correlation takes the values close to 0, around 0, we can actually talk about the lack of the correlation between the variables' values. And positive coefficient indicates a general positive upward sloping relationship, whereas a negative coefficient of correlation indicates in general an opposite relationship. Like here coefficient equal to 1 means ideal linear relationship between the values of the variables. And now we decrease the value of R coefficient. Now it is equal to 0.7, and as you can see, we can perceive a general tendency, yes, here, but the linear relationship is significantly weaker, yes. And now we have R coefficient equal to 0.3, and we can also perceive a general trend by but the deviations of observed values from this a line that represents the linear relationship between the variables are significantly higher. Yeah, the deviations from an ideal line are much higher. And here we have coefficient close to 0. Yes, we can't actually perceive any general trend here. Here we have -0,3. Yeah, we can perceive a regularity here, of course, negative regularity, but of course these deviations are higher than in this case. Yeah, and here we have ideal linear relationship between y and x values. Yeah, so that R coefficient here is equal to endpoint -1. And here statisticians propose an interpretation of R coefficient. Around 0, no correlation. From 0 up to 0.2, very weak correlation, and so on, up to perfect, ideal correlation. And statistician beginners, remember that rule. Correlation does not imply causation. Yes, it's something different. It's something different. Here we have an example of a fake correlation. Yeah, here we consider two variables: US spendings on science, space, and technology, and another variable from completely different area of life: suicides by hanging, strangulation, and suffocation. Yeah. And as you can see, data shows very strong, almost ideal correlation between both variables. But in the reality, actually, absolutely, there is no connection, yeah, between spendings on science and hanging suicides. Yeah. In my opinion, we didn't capture an important factor that has an influence on US spending on science or suicides by hanging, strangulation, suffocation. But actually there is no real connection between the variables. This phenomenon is called spurious correlation, and you can find some more examples here. So, as you can see, this little kitty is taking advantage of that phenomenon. But I'm sure that this little kitty is a cause of spilled feed. And the last measure is coefficient of determination, which is also called R squared. It shows the degree in percent of interdependence between the values of statistical variables. Yeah? Remember, covariance indicates us the direction of interdependence between the values of statistical variables. R coefficient gives us the information about the direction and strength. Yeah? R squared coefficient gives us the information about the strength of interdependence between the values of statistical variables, and it's very useful fact that this strength can be expressed in percent. For example, if R squared is between the values of attribute between values of variable x and values of variable y is exactly equal to 0.75, it means that the variable x values or variable y describe the variability of the variable y values in 75%. Remember that we don't indicate which variable is cause, which variable is an effect. Yeah? We are talking about the interdependence. So the variability of x values explains the variability of y values in 75%, and simultaneously the variability of y values explains the variability of x values in 75%. The construction of this measure is very simple. We raise coefficient of correlation to the power of 2. This is squared coefficient of correlation. Yeah, R squared. Yes, so it is why we call it R squared. Task 1. A table below compiles the real data about GDP per capita, it's our variable x, measured in 1000 zlotys per inhabitant, and variable y, number of enterprises per 10,000 inhabitants in chosen regions of Poland in 2017. Okay, what do you think about the relationship between GDP per capita and number of enterprises per 10,000 inhabitants? In my opinion, there exists a relationship between both variables. Why? Because high level of GDP per capita means high level of the output, or high production level per inhabitant. Why do we observe a high production level per capita in a particular region? One of the reasons is there are lots of firms, high number of firms that perform in a particular region. Yeah, they manufacture their products, they offer their services. Yeah, so they rise GDP. So in my opinion, there is a strong positive correlation between both variables. Let's check it out. The first step in this kind of data analysis is to find a covariance. As you remember, covariance between variable x and variable y values is the average product, yeah, from I equal sum from I equal to 1 up to n, and here we have the products of the deviations between variable x and variable y values from their mean, the average product. Of course, we can also utilize a transform formula, which is, for me, much more effective. Yeah, it is the sum from I equal 1 up to n of the product of variable x and variable y values. Yes, this is the average product of variable y and variable x values minus mean x and mean y. Yeah? All right. So here, the only thing that we need is the product, yeah, between xi and yi. So we need to construct the column with the product xi multiplied by yi. Actually, we have here 6 products. Yeah. In this column, we will multiply the column of x by the column of y. In the first row, we have 57.3 multiplied by 1271. Yeah, and the result is 72828.3. Okay. In the next row, we multiply 41.9 by 940. It is 39,386. And so on. The next values are following: 29773.8, 47508, 4763.3, and finally 53,023.3. Okay. And the next step is to summarize the column of the products and actually also the column of x and the column of y. The sum of the values from that column is 290,282.7. Yeah, I am very accurate here, like Excel. Yeah, because I used Excel here. And here we have the sums like 273 and 6,269. Yeah. As you can see, we need to obtain, we must ensure here in the formula mean values of GDP per capita and number of enterprises per 10,000 inhabitants. Here we have also the mean product. Yeah, the mean product. It means that we need the next row, in which we will compute mean level of x, mean level of y, and mean level of the product. First goes mean level of x. So we divide 273 by 6. Yeah, 273 by 6, and the result is the mean level of GDP per capita 45,000 517 zlotys per inhabitant. Okay, and the mean level of number of enterprises is 1044.833 enterprises. And the mean product of variable x and variable y values is 48,380.45, and this number is an effect of dividing this number by 6. I will write it down. Here I utilize this formula. Here we have the sum of the products of x and y values. This sum is equal 290,000, 282.7. I divide this sum by n. This is the population size. We distinguish 6 regions, so I divide this sum by 6, minus mean level of x, 45.517, multiplied by average number of enterprises per 10,000 inhabitants, 4.833. Yeah, 290,000, 282.7 by divided by 6, it's 48,380.45 minus 47,557.664, and the final result is actually, here we have approximation. Here the final result is 822.786. This is the value of covariance measured by 1,000 zlotys per inhabitant multiplied by number of enterprises per 10,000 inhabitants. Yeah, we multiply the unit of variable x by the unit of variable y. Here we have 1,000 zlotys per inhabitant. Here we have number of enterprises per 10,000 inhabitants. Yeah, and how about the interpretation of this amount? The interpretation of this measure is following. In general, yes, we start with the in general. High, in bracket low, because we can say it simultaneously. High level of GDP per capita means high, in bracket low, level of number of enterprises per 10,000 inhabitants. Yeah, because covariance is positive, so here we have indicated the direction of this relationship. The direction is positive. This is a positive number. So it means that if we observe a high level of GDP, we simultaneously, in general, of course, observe high level of the number of enterprises per 10,000 inhabitants. In other words, we can say that if we, in general, if we observe a low level of GDP, we also observe the low level of number of enterprises per 10,000 inhabitants. Okay, and the next measure that we need is the coefficient of correlation. Coefficient of correlation. Coefficient of correlation, Rxy, is a ratio between covariance and standard deviation of variable x and variable y values. We know the covariance, it is equal 822.786, and now we have to compute standard deviation of GDP per capita in chosen regions and standard deviation of number of enterprises per 10,000 inhabitants in chosen regions. As you remember, first step in computing standard deviation is to compute the variance. The variance of x can be written down by the formula, the sum from I equal 1 up to n of xi squared values divided by n minus mean value squared. Yeah? It means that in the next column I need squared values of x. Squared values of x. Squared values of x. So here I raise the value 57.3 to the power of 2. Yeah. And the result is 3,283.29. Yeah. And in the next column, in the next row, 41.9 is squared, and we receive 1,755.61. And the next values are following: 49, 1,831.83, 84, 2,313.61, 2,237.29. Yeah? And according to Excel, the sum of that column is 12,696.13. Yeah? Your results can differ a little bit from the Excel results, yes, because Excel is the Excel accuracy is very high, and the mean square of variable x values, mean square of GDP per capita in chosen regions in Poland, is 2116.022. Okay, we can utilize this information. We will compute the variance of GDP per capita values, here we have mean squared value of GDP per capita, 2116.022. Yeah, here I divide 12,000 blah 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 by 6, and I receive 2.116.022 minus squared value of 45.517. Yeah, and here variance is equal to 44, of course, approximately is around 44.255 thousand zlotys per inhabitant squared. Yeah, and finally standard deviation of GDP per capita values in chosen regions is a root of 44.255. Yeah, and here the root is around 6.652 thousand zlotys per inhabitant. Yeah, so it means that the average deviation of GDP per capita values from the mean is around 6.7 thousand zlotys per inhabitant. Yeah, the average deviation of GDP per capita in chosen regions in Poland from their mean is around 6.7 actually thousand zlotys per inhabitant. Okay, we can do the same thing on the basis of variable y, but it is a boring activity, so I will give you the final result, the standard deviation of variable y values, the standard deviation of number of enterprises per 10,000 inhabitants. Yes, you can check it out in home. It is around 141.024. So the average deviation of number of enterprises per 10,000 inhabitants in chosen region of Poland from the mean is around 141 enterprises. Yeah. Okay. And finally, we are able to compute the famous coefficient of correlation. It's a ratio between the covariance and the product of standard deviations. In the nominator, we have 822.786. And in the denominator, we have what? 6.652 by 141.024. And finally, we have the value of R coefficient, coefficient of correlation at the level of 0.877. 0.877. This amount has no unit. Yeah. We can interpret that amount using a cheat sheet from the previous slide, as you can see, the value between 0.8 and 1 means very strong correlation. So I can interpret it using the following words. We observe what? We observe very strong and positive correlation between GDP per capita and number of enterprises per 10,000 inhabitants in chosen regions of Poland. Yeah? Once again, there exists very strong and positive correlation, as we expected, very strong and positive correlation between GDP per capita and number of enterprises per 10,000 inhabitants in chosen regions of Poland. Yeah? And the last step, the last measure is R squared coefficient. R squared coefficient, as you can see, is very simple. It is enough to compute a square of that amount. We will receive R squared coefficient. So it is 0.877 squared, and the result is 0.77 approximately. Okay, and how about the what about the interpretation of that measure, 0.77? What does it mean? It means that the variability of GDP per capita, in bracket we can write down the second variable, because we, as you remember, we don't indicate which variable is a cause and which variable is an effect. We don't do that. Yeah, so we can say it in both versions: the variability of GDP per capita, or number of enterprises per 10,000 inhabitants, the variability of GDP per capita, or second variable, values, explains the variability of number of enterprises per 10,000 inhabitants, or in bracket GDP per capita, in around 77%. Yeah, the variability of one variable values explains the variability of the second variable values in 77%. Yeah, we don't indicate which variable is a cause, which variable is an effect. Task 2. 8 respondents have been asked about 2 questions. First question: is how many hours you spent in the front of TV per week. This is variable x. Here we have the column of x. And the second one is how many books you have read during the year, variable y. What do you expect? What do you expect here? What you can say about the possibilities of the relationship between time spent in the front of TV and the reading abilities? In my opinion, okay, it may be a moderate correlation between the time spending in the front of TV and reading books, but I think it has a negative, rather negative character. Yeah, it means that I expect that people who spend a lot of time in the front of TV read a smaller number of books. Yeah, so I expect here a negative relationship, but in my opinion, this relationship is relatively moderate. Yeah, moderate, not strong. So let's check it out. Yeah, let's quantify the problem using covariance, correlation coefficient, and R squared. As you remember, covariance between x and y values it can be denoted using the second type, the second transformed version of formula, xi multiplied by yi divided by n minus x mean multiplied by y mean. Okay, in the first step, we need what? We need the products between the values of x and the values of y. The first respondent spent 3 hours per week in front of TV, and the number of books that this respondent have read is 6. Yeah. So the object 1 is characterized by the value of x equal to 3 and the value of y equal to 6. First column, xi multiplied by yi. 3 times 6, 18. 16. 8 times 2, 14. Yeah? 0, 20. 35, 70, and 105. 100 and 0. Yeah, 100 and 0. Okay, I'm a little bit lazy, so the sum of that column is 273. I saw it before, yeah? 273. Okay, the sum of the values of time spent in the front of TV is 124, and here we have the sum of all books that have been read, 75, and the mean value 15.5 and 9.375, and here the mean product is 34.125. Yeah, we divide these numbers by 8. 124 divided by 8 is 15.5. 75 divided by 8 is 9.375, and 273 by 8 divided by 8 is 34.125. Okay, and in our example we have 34.125. It's the average product. It's the average product of x and y values minus 15.5 multiplied by 9.375, and then the correlation, the covariance between reading abilities and time spent in the front of TV is minus 111.188 according to Excel. Yeah, this time is measured maybe by how many hours? Yes, so hours per week. Yeah, and here we have the unit, how many books? Yes, in pieces during the year. Yeah, or maybe hours, simpler hours and pieces. Yes, so here we have hours multiplied by pieces. Oh, this is okay. Okay, how about the interpretation of that amount, of the interpretation of covariance here? We can perceive a negative relationship, interrelationship between time spent in the front of TV and reading abilities. And in general, we can write it down. In general, high in bracket low amount of time spent in the front of TV means low in bracket high. If we start with low, here we will repeat high. If we start with high, here we repeat low. Means low in bracket high number of books read. Yeah, high level of, in general, high level of one variable means low level of the second variable, and inversely, low value of one variable means high level of the second variable. Okay. The second measure is coefficient of correlation. As you remember, this is the ratio between variance and the product of standard deviations. We need standard deviations of time spent in the front of TV and number of books read. So here I need square values of both variables. Yeah, it's very easy. 964 196, yes, 019 625, and of course 4900, and here 36 41 49 4035 is squared is 1225, 16 and 0, of course. Yeah, and the partial results are following the sum of all squares of time spent in the front of TV is 5804, and the mean squared value of time 725.5, and here respectively we have 1731 and 216.375. Start with the variance of x. As you know, it's the sum from I equal 1 up to n. We have 8 observations, 8 respondents, so n is equal to 8. The sum from I equal to 1 up to 8 of xi squared divided by the population size minus mean value of x squared. In our example, mean square of x values is 725.5 minus 15. This is the mean value, 15.5 squared, and the result is, according to Excel, 485.25 hours squared. We can also compute the variance of books read. This is the sum from I equal 1 up to 8 of yi squared divided by n minus y squared, mean value of y squared. The partial results are following: 216.375 minus 9.375 squared, and the result is around 128.484 pieces squared. Okay. In the formula I'm using standard deviations, so I need a root of both values. The standard deviation of time spent in the front of TV is 22.028 hours, and standard deviation of number of books read by the respondents is 19.335 pieces. Okay, And now we can move on to coefficient of correlation computation. Covariance between both variables values is minus 111.188, and we divide this value by the product of standard deviations. 22.028 times 11.335. And now we will see the strength. Yeah, we know that the interrelationship is negative. Now we will know the strength of this interrelationship. The strength of this interrelationship is around minus 0.445. 445. Okay, let's compare this amount with our table. Here we back to the previous slide, and we see that here the module of that value is placed between 0.4 and 0.6. So it means that we are dealing with moderately strong correlation. Yeah? So here we observe moderate strong and negative. Yeah, moderate strong. So it is what we have expected. Yeah. This correlation is only moderately strong. Yeah. There is a relationship, but is moderately strong. Okay, and of course we are able to compute R² coefficient. We will raise the coefficient of correlation to the power of 2, so we square that, and how about the variability explanation? It is 0.198. Yeah, around 20%. We can write it down. Yeah. And the main conclusion is the variability of one variable, the variability of the values of one variable explains the variability of the values of another variable in 20%, in around 20%. Yeah. The variability of time spent in front of TV explains the variability of number of books read in 20%, and inversely the variability of number of books read explains the variability of time spent in the front of TV in around 20%. And the last task. 70 regions have been examined in terms of variable X, industrial output in million zlotys, and variable Y, an unemployment rate in percents. The partial results were as follows. the sum of the variable x values equal to 542.5. Okay, let's write it down using mathematical operators. The sum from I equal 1 up to 70, yes, because here we have examined 70 regions. Yeah. Alright, so the population size is 70. The sum from I equal 1 up to 70 of xi, yes, because this is the sum of all values of x, is equal to 542.5, and we know that this is variable is measured in million zlotys. Okay, average square of variable x values is equal to 89.33. Average square is the sum from I equal 1 up to 70 of squared values divided by n, the population size, divided by 70. Yeah? Alright. Average square. This is the sum of squares. This is the average square. Sum of squares, average square of variable x values is 89.35. The next information is the sum of squared variable y values equal to 354.5. Okay, so I can write it down using the sum from I equal 1 up to 70 of yi squared values is 354.5. Mean value of variable y values, mean value of unemployment rate is 1.6, of course percents. Here we have percent squared, and here we have million zlotys squared, because here we have a square. And the sum of the product of variable x and variable y values, the sum from I equal 1 up to 70 of the product between variable x and variable y values. Yeah? Did you catch that? Is 421.6. Yeah. Okay, we have recognized all the partial results, and now we are able to compute first covariance. We need to have a use of these partial results. Covariance between industrial output and unemployment rate is the sum from I equal 1 up to 70 of xi yi divided by the population size minus mean value of x and mean value of y. Here we have mean value of y, I need mean value of x. Mean value of x is the sum from I equal 1 up to 70 of all values of x divided by 70. Here we have the partial results that is necessary here. So we divide 542.5 by 70, and we will receive the following result. 542.5 divided by 70 is 7.75 million zloty. This is the average industrial output in investigated 70 regions. Okay, let's back to the covariance. Here we have the sum of the products, 421.6. On the margin, the unit of the sum of the products is million zlotys multiplied by percent. Yeah, it has no sense, but this is the unit of the product. Divided by 70 minus min x 7.75 multiplied by min y is 1.6. Here we divide 421.6 by 70 is around 6.023 minus, and we need the product of 7.75 times 1.6, and this is 0.4. Okay, and now we have computed covariance 6.023 minus 12.4. It is minus 6.377. This is our covariance. It's negative, so we are dealing with negative interrelationship between industrial output and unemployment rate in investigated regions. We can say in general high or low values of industrial output means low in bracket high unemployment rate. In these regions. In general, high values of industrial output means low unemployment rate, and inversely low values of industrial output are accompanied by high unemployment rate. Okay, the next measure is coefficient of correlation. Coefficient of correlation is the ratio between covariance and the product of standard deviations. Here we have some partial results that help us in coefficient of correlation computation. The variance of x, as we know, is the sum from I equal 1 up to 70 of squared xi values divided by the population size minus mean industrial output squared. In our example, this sum is this average square of industrial output. Average square of industrial output. Do you see that? Here and here we have the same thing. The same thing. Average average squared industrial output is 89.35 minus, here we have average industrial output 7.75 squared. 7.75 squared is 60.063. So here the variance of the industrial output is 89.35 minus 60.063. 29.287 millions zlotys squared. This is the variance of industrial output in analyzed regions. And standard deviation here is the root of variance. Okay, but my calculator abilities ends here. Yeah. Dear Excel, my old friend, the standard deviation of the industrial output is approximately 5.412 according to Excel. Yeah, millions zlotys, of course. So it means that the average deviation of industrial output from the mean is around 5.4 million zlotys in analyzed regions. Okay, you can find the variance of unemployment rate, which is, dear friends, 1.582. Yeah, please check it out at home. You have to repeat all the procedure. Okay, and in my computation, I'm taking into account covariance value minus 6.377 divided by the product of 5.412 and 1.582. Okay, and the result is minus 0.745. Minus 0.745. Yes, so once again, we have received a negative correlation between the variables, and this correlation can be treated as strong correlation. And according to the voice of statisticians, we are dealing with strong negative correlation between both variables. Yeah? So in the regions where we have high values of industrial output, the unemployment rate is relatively small. Yeah? And the regions in which we have high unemployment rate are characterized in general by a low value of industrial output. Yeah, the economic activity of that region is relatively small because low industrial output are accompanied by high unemployment rate, of course, in general. It has sense. It has sense. Okay, and the last one is coefficient of R-squared coefficient. R-squared coefficient. R-squared coefficient here is a square of 0.745. Here we have 55.5% approximately. Yeah. It means what? It means that the variability of industrial output values explains the variability of the unemployment rate in 55.5%, or the variability of the unemployment rate explains the variability of industrial output values by 55.5%. Thank you.